Okay, definite integrals and their antiderivatives. This is section 5.3, and I have on this PowerPoint for you 7 problems that I want you to find their derivatives. We need to continue getting practice with finding derivatives. These 7 problems will be due tomorrow when you walk in the door as a 7-point quiz grade. If you did not happen to watch this video, then you are out 7 points, which is not good. So you can pause it, find your 7 derivatives, and then move on. What we're planning on learning about, definite properties of definite integrals. This is a huge concept in this section. The average value of a function, the mean value theorem, which follows the average value of a function, and connecting differential and integral calculus. Working with the properties of definite integrals helps us to understand better the definite integral itself. Connecting derivatives with definite integrals sets the stage for the fundamental theorem of calculus, which is the next section, which is the whole basis of calculus, really. Page 269 in your book gives rules for working with integrals. The most important ones we're going to talk about are the following. The first one is the integral from a to b of f of x dx is equal to negative the integral of b to a of f of x dx. If you just flip-flop your upper and lower limits, then all you have done is just found a negative area. Okay, so if we're going backwards, we're finding negative area. This one should make pretty good sense. The integral from a to a of f of x dx would be 0. If your upper and lower limits are equal, then the integral is 0. That should follow, right? The integral from 0 to 0, well, there's no area under the curve to find, so it's just 0. Next one, the integral from a to b of k, a constant, times f of x dx. We talked about this briefly a little bit before, but you can move that k to the outside, like so, and then just find the integral from a to b of f of x dx. The constant multiples can be moved to the outside. Number 4, if you have two functions that are added or also subtracted together, you can split them up into their own integrals. So the integral from a to b of f of x plus g of x can be split up to be the integral from a to b of f of x plus the integral from a to b of g of x. They are allowed to be added and subtracted. Just like integrals can be added and subtracted, intervals can also be added or subtracted. So the integral from a to b of f of x plus b to c of f of x would then be equal to the whole entire integral from a to c of f of x. So if these two limits b match, then you can go ahead and combine them as one integral, and that is shown right here. If I have this function, I have a, b, and c listed on here. There's the integral from a to b. Here's the integral from b to c, and that would be equal to that whole entire area from a to c. So you have these 3 problems to do using your properties, and you know this information up above. The integral from -1 to 1 of f of x is 5. The integral from 1 to 4 of f of x is -2. And the integral from -1 to 1 of h of x is 7. If you know these 3 facts, are you able to find these 3? And if you are, then actually find them. So I want you to find the answers to these 3 questions. Some of them may be possible, some of them may not be. When you're done, add that to your other 3, your 7 derivatives. You will then have a 10-point quiz grade tomorrow when you walk in the door. Average value of a function is the value that would give the same area as if the function was a constant. And I have down here a link to the site where the man was discussing issues with us last time. And I think his discussion here is a very good one. So if you want to look at that, that's great. If not, I'm going to try and use the same terminology as he did in this. But let's just say that we had the function y equals 1/2 x squared. It should make sense to you that the area under the curve of that function from 0 to 3 would be the integral from 0 to 3 of 1/2 x squared dx. If I found that answer, that would give me the area that lies underneath that curve. Now, what they did here is they found the antiderivative, and then they used the fundamental theorem of calculus to evaluate that antiderivative. We will get into that later, but here's how they did it, and then they ended up getting 27 over 6, which reduces down to 9/2. That is the area under the curve. If I wanted to find the average value, I will take the area under the curve, and I'm going to divide it by the width of my interval, which is 3 units, and get 1.5. What that 1.5 represents is if I would take all of this area and kind of pack it in to where it now settles to a constant level, that level would be 1.5 units. And the way the man in the video describes it is, let's pretend that we have a vase of water or something, some body of water, where if I pour it in and it has this shape, as it settles, where would it settle, at what level would it settle to? That level is your average value. And you always, we get average by adding up all our numbers and dividing by the number of numbers we have. Well, that's kind of what we're talking about here. Adding all the numbers is finding the area. So we're finding the area of underneath the curve. That's like adding all our numbers up, and then we are dividing by however many numbers we have. That's from 0 to 3. So all average value is your area divided by the width of your subinterval. So here is the actual formula that you will see. 1 over b minus a times the integral from a to b of f of x dx. Okay? The mean value theorem for definite integrals says that for a continuous function, at some point on the interval, the actual value will equal the average value. So here is the mean value theorem. It says if the function is continuous over a to b, then there will be some point c in a to b where the function actually does take on that average value. So if I go back here, the mean value theorem says that, oh, look, it does occur, and it occurs at this x value, which is about, 1.7 or whatever. That's what the mean value theorem for integrals says. If I find the average value, there has to be a place on my function where it equals that average value. Just make sure you remember that average value is still the area under the curve, but you're just making sure you multiply by 1 over b minus a or dividing by b minus a. Either way, it's the same thing. So we are going to find the average value of this function, 2 minus x squared, on the integral from 0 to 4. Here is my formula. We will oftentimes see AVG of f here. That means average value. My formula is 1 over b minus a times the integral from a to b of f of x dx. I just plug in all my values. Here is my a and my b, 0 and 4. I put them in. My function is 2 minus x squared. And then we just use the calculator to evaluate that integral. And at the beginning, you can just type in 1 divided by 4 minus 0, which is just going to be 4. And then I'm going to multiply it by my integral. So I just go down to number 9. And then I type in from there my function with respect to x. My lower limit is 0. My upper limit is 4. And we get negative 3 1/3, which you see your answer to be negative 10/3. Our last concept that we're going to discuss is called the derivative of an integral. Let's kind of go back to some very elementary concepts. Every operation in math has an inverse operation. So for example, division's inverse operation is multiplication. Exponential's inverse operation are logarithmics. Sine's inverse operation is called inverse sine or arc sine. Just like integrals are an operation, he also has an inverse operation of derivatives. Integrals and derivatives undo each other. So if I was to ask you to find the derivative of the integral from a to x of f of t dt, the derivative and the integral will cancel each other out because they're inverses of each other, and what I'm left with is the actual function f of x. Now notice that there are t's here, because if we have an x up here, we'll discuss this a little bit more with the fundamental theorem of calculus. If I have an x up top as my upper limit of integration, I just don't want to put another x in my f of t dt here. I don't want this to say a to x of f of x dx. So we just put a dummy variable or just another variable in to show that my variable I'm discussing is my upper limit, actually. Don't let that confuse you too much. We'll talk more about it a little bit later. But what I want you to understand is that if I'm asking you to find the derivative of the integral of the function, my answer is the function, because my derivative and my integral cancel each other out. We are going to talk a little bit more extensively about that tomorrow. So when you come in tomorrow, you need to make sure you have your 10-point quiz that will go as a quiz grade in your Into Progress book. And we'll also start discussing things about 5.3 tomorrow in class. Have a good day, everybody. We'll see you later.